Welcome to lesson 3 of chapter 7, Trigonometry and Modelling from Year 2 Pure Maths. And today we're going to be putting together the ideas of compound angle formulae, which are identities, of course, and the double angle formulae, which we derived from those compound angle formulae. And we're going to use them in a problem-solving context with proving other identities and also solving trig equations. And as usual, there's the prerequisites, the preparation work, which is, of course, the year 1 trigonometry and algebra, and going back to GCSE and even pre-GCSE algebra, surds and trigonometry. Right, okay. Please pause the video and have a go at the 4 warm-up questions. Okay, and let's have a look at the solutions. All right, so for question 1, it's a classic factorization that you've done probably thousands of these now. It's an A is 3 situation, so I'm going to do this by inspection. I've separated my brackets already, and I need to set up the rest of the binomials, if you like, to create the plus 5x and the negative 2. So I know I'm going to get 3x squared from what I have already. So in order to get the plus 5x, and if we look here, we've got a negative 2 on the end. The only real factors I'm going to be using are 1 and 2, obviously with signs alternating, negative and positive. So I'm looking at probably a plus 6x, subtract an x here. To get the plus 6x, I'm going to need to have a plus 2 in the second bracket, and to get the x taken off, I would need to have a negative 1 there. And I'm sure you've got your own ways of doing this. All right, and if you have time, obviously just do a quick check, make sure you've got that right. So if we do 3x multiplied by x, that's of course 3x squared. This will give me plus 6x, a negative x there, and the negative 2. So it all seems to check out. So I've just used the lobster claw method there. And moving on to question 2, we're given that cos theta is, of course, a half. All right, so that's a fixed value. And what we're told now is to use an identity. Now, this identity is legitimate. Yes, it's not made up. This is something we can prove later. But cos 3 theta can be represented as 4 cos cubed theta subtract 3 cos theta. So I'll be showing you how to do that later. And what we need to do now is use this to find the value of cos 3 theta. Well, it's a substitution, isn't it? So we know, I'll just write it down again, that cos of theta is, of course, 1/2. Notice I'm not interested in finding out theta. That's not the objective. It's just to find out the cosine of 3 theta. Right, so let's use the identity. So therefore, cos of 3 theta is going to be 4 lots of cos theta, which is, of course, a half. I'm going to use a substitution. But the half is going to be cubed. Okay, because obviously cos theta cubed we write as cos cubed theta. Okay, and then we subtract 3 lots of the cos theta as well. So that's 3 multiplied by 1/2. Okay, and then we just have to tidy this up. And obviously we've talked about this before, but the naive approach would be to multiply the cos theta by 3, which is obviously not going to be true. You would have 3 over 2 there, which is outside the range of any cosine graph with a multiple inside the function. So remember that 3 here, just going on a bit here, but the 3 inside the function doesn't change the range. The range of cosine is still going to be between -1 and 1 inclusive. All right, so just want to make that clear. All right, and let's carry on in green. Why not? So 4 lots of 1 over 8 subtract 3 over 2. Now 4 over 8 is of course a half, so we have 1 half subtract 3 over 2. So we have a half subtract 1.5 essentially, which is going to be -1. So there you have it. And is there a different way of doing this? Well, do we know what cos theta actually is? Well, yes, we do. But could we deduce this result from finding out what theta is? Yes, you could use a cast diagram perhaps, but because we've got the substitution all set up, I think that will do. So the answer is -1. All right, so questions 3 and 4, we're going to employ a bit of detective work here. It's identity spotting time. So we'll start with question 3. And the idea behind this, and it's made easier by the fact that we are involved in a trigonometry lesson, aren't we? So you're anticipating using the identities because that's what we're talking about. So does this look like an identity we've met before? Well, with a little bit, maybe a bit of flicking through your notes or looking in the formula booklet, you'll probably notice very quickly that this is, of course, the cosine double angle identity. So I'm going to write it like this. So cos 2a is identical to 1 subtract 2 sine squared a. And I've just made a faux pas there. Of course, this is not given to you in the formula booklet. It's the compound angle identities that are. You would have to know this from memory. So a good reason to get all this stuff committed to memory is simply because you're going to be having to identify things like this in this question. And if it's not at the forefront of your mind, then you might miss it. So I'm gonna say it again and make it look really important. You're gonna have to remember these double angle identities. Okay. So let's have a look what we've got. Well, it's the right hand side, isn't it? That's in the form we need. So in my identity in the question, I've got 1 subtract 2 sine squared pi over 7, like this. If I just match them up, essentially, we can now see that the A is worth pi over 7. Okay. And we have to write it as a single trigonometric function. Well, we can now use the left-hand side of the identity here, and we can now state that hence cosine of 2 pi over 7 is our answer, isn't it? So that's now a single trigonometric function. Single as in it's not got any other terms to worry about. So that's our answer. So I'm going to make that look nice, and you can evaluate that if you want to, but it's not required. It just asks you to write it as a single function. And if we move on to question 4, we have similar situation, identity spotting, and with again a bit of looking up, or if you've learnt them, fantastic. You should see very quickly that this is the sine double angle formula. So sine 2a, which is identical to, in fact, I won't use a again, I'll use b, so we're not confusing things. Sine 2b is identical to 2 sine b cos b, like that. And let's make that look important as well. So while we're making it look important, we can see by matching them up that the value of b, or b itself, can be substituted with pi, not pi, sorry, I beg your pardon, theta over 4. Yeah, if we just sort of match those up. So I'll do it in the same way. we have 2 sine of theta over 4 cos theta over 4. So therefore, B is worth theta over 4. And we're never going to be able to work this out unless we're told what theta is. We can't evaluate it. But what we can do is state that hence we're going to have sine of 2 theta over 4. We're going to double it, which simplifies to sine of theta over 2. So it's sine of theta over 2, all that. Which makes sense, doesn't it? Because it's a double angle identity. And these theta over 4s are half of what we have here. Okay, so that concludes the warm-up. All right, so let's get straight into it with some worked examples. So we have a classic trig equation, and we're solving in the interval from 0 to 360, which we like because that's in degrees, so that's really familiar. And we've got an equation set up, and on sort of first glance it looks innocuous, and then on closer inspection you'll notice that we have theta and 2 theta simultaneously within the same question. Now, we've not seen this before, so the question is, we need a strategy, or what strategy can we use in order to make this soluble, because we can't have a theta and 2 theta. We have to be using the same object. Okay, it's not like collecting like terms with algebra. These are variables that have functions attached to them. So what can we do? Well, we go to our trusted identities. After all, that is the theme. So we look at this and think, I can break this open using an identity. So let's just write a little list of all the things we need. In fact, it's just one thing, isn't it? So we need the cosine double angle identity. So let's write them down. So we've got cosine of, let's use A again. Or actually not, let's use the context of the question. Let's go back to theta. So cosine of 2 theta, and let's just write out all the triple angle what am I talking about? All the double angle identities for cosine. And this is where the problem arises, isn't it? Because unfortunately, there's not just one, there's 3 to choose from. So let's write them out. So the first one is, of course, cos squared theta, subtract sine squared theta. And don't worry, if you choose the wrong one, it's not a disaster. You can always recover later, okay, once you spot the problem. And the last one, 1 subtract 2 sine squared theta. So this is our summary of identities. Okay, now going back to the question, notice that the other term, which is also very important in this equation, is a sine, okay? Sine function. And you'll remember from previous trig equations, particularly when they are basically quadratics in disguise, you take the linear term, and that's what you have to convert your squared term into. Now, in this situation, it's probably even more obvious because I know I'm going to have to replace my cos 2 theta here with any one of these identities. Okay, I've got to choose one, and ask yourself the question, or say it, or I'll ask you, and you can sort of say the answer to yourself. Which is the one that we need? Well, now you've had a think about it, it's probably going to be strikingly obvious that we're going to use the bottom one. And what is the reason? Well, if we use the bottom one, we'll have everything in terms of sine theta, okay? As indicated or hinted at with a little nudge and a little wink by that term there. The sine theta is telling us, get everything in terms of me. So let's write out our equation. So starting doing some proper work now. So we're going to have 10 sine theta subtract 3. And I'm going to replace this with the identity at the bottom here. So I'm going to open some brackets, and I'll use a different color to show the substitution. 1 subtract 2 sine squared theta. Close that bracket. And that's equal to 1. And notice we've solved the problem that we had initially. Everything is now just theta. There's no 2 thetas anywhere to worry about. So it's the same object that we can solve for. Let's expand and simplify. So therefore, 10 sine theta, subtract 3, and then remember we've got a negative multiplied by a negative, so that's going to be plus 6 sine squared theta is equal to 1. And collect like terms, we'll get everything onto the left-hand side simply by subtracting 1 from both sides. And I'm going to put them in quadratic order, traditional quadratic order. So we're going to have 6 sine squared theta, add 10 sine theta. Okay, and then if we're subtracting 1 from both sides, I'm going to have negative 4 subtract 4 equals 0. Okay, and you'll notice this is the classic trig quadratic, isn't it? And we've added just a couple of layers of new information here, new knowledge that we've not really applied before in this situation. So let's carry on. Now, if you're comfortable with this, go ahead and factorize it as it is, if you want to. If you're not comfortable with it, use a substitution. But before we do that, there's something else we can do. You'll notice, of course, that each of the coefficients, and this is worth checking every time you do a question like this, they're all multiples of 2. So we can actually divide the whole equation by 2 and get something a little bit more simplified. Okay, so if I divide by 2, we're going to have 3 sine squared theta added to 5 sine theta. Okay, and then subtract, divide that by 2, so that's going to be 2. And that's going to equal 0, isn't it? Okay, now the eagle-eyed amongst you will have recognized this from earlier. This is warm-up question 1, isn't it? The only difference, of course, is that I have sine instead of x. So let's just make a substitution. Let big X equal sine theta. So therefore, we're going to have 3 x squared plus 5 x subtract 2 equals 0. And we factorized that already. So therefore, we have 3x and x like that. Well, we've already done it, haven't we? So that was plus 2 and subtract 1 there. Okay. So our solutions are, I like doing my therefores. So x is going to be equal to 1/3, or x is going to be equal to -2. Okay, and then we can sub in our sine theta again. Remember, we've made a substitution. We've not solved the equation yet. So let's do that. So we're going to have sine of theta is going to be equal to 1/3, or sine of theta is going to equal -2. All right, now we have some solutions. Now, this is where we have to use some knowledge, isn't it? So we have two options, 1/3 or -2 to represent sine theta. Again, we've got to be careful, because those of you who'll know about your domains and ranges will know that this one here has no real solutions. Okay, it probably has complex solutions, but not real ones. So we'll discount that simply because sine can never be less than -1, and it certainly can't be bigger than 1 either. So that can be discounted. So the only equation we need to solve is for sine theta to equal 1/3 and in the range from 0 to 360. And we're back in year 1 territory now, aren't we? We've got a nice equation we can solve pretty simply. So I'm a bit annoyed I've just used the middle of the board for this, but what I will do, I'll do a nice cast diagram on the left-hand side where there's a bit of space. So let's just go back up here. And we should have enough space for this. So we'll get our principal angle. Principal angle. So do that first so we know what we're putting on the cast diagram. So that's going to be theta. In fact, I won't write it there. So I've got my arrow in the way. So theta is going to be the inverse sine of 1/3. Which is equal to, okay, sorry about the pause there. So that's going to be the inverse sine, okay, I'm just checking I'm in degrees, which I am, of 1/3, just come out of that bracket. There we go. So that's 19.47, okay? And I'll round it to 2 decimal places because I'll probably want the answers to 3 significant figures if it's not specified. And what I will do, I'm just going to erase this arrow so I've got a bit more space. So 19.47 degrees. Okay, and we can now add our 19.47 degrees to our cast diagram. I'll do that here. You've done this so many times now. Such a useful diagram. Okay, and if we go back to the question in the red box just here, we can see that the value of sine theta is, of course, a positive number. It's positive 1/3. So we can use the positive quadrants for sine, which are, of course, A and S. That's where sine is positive, which you all know. So let's add the 19.47 there. And the 19.47 degrees there. Just put my degree sign on. Okay, and we can now write down the answers. So just cancel that. I hope this is making sense, guys. So for our final answers, we're going to have theta is going to just be 19.5 essentially to 3 significant figures. And then we're going to have to subtract that from 180. And if you don't like doing mental arithmetic, so let's do it on here. 180 subtract 19.47. I'll go back to that. Okay, so that's going to be 160.5. Okay, let's get rid of that. Let's write it here actually. So that's 160.5 degrees. All right, and yeah, we've got the 2 answers. We've got 2 answers between 0 and 360, and we've solved the equation. So example 2, we have not quite as much room to play with here. And you'll notice an issue straight away. We have 2 different trig ratios in front of us. We have sine and, of course, one of our new ones, sec. Okay, so we're going to need to just make a note of what sec actually is. Just going back on, or going back over some of that work we did on reciprocal trig functions. So you'll remember, of course, that sec theta. Oh, I don't like that writing. Sec theta is identical to 1 over cos theta. And how you do remember this, of course, a bit of revision. Well, it's that 3rd letter rule, isn't it? So the 3rd letter of sec corresponds to the 1st letter of its reciprocal, which is of course cos. And it's the same for cosec and cot, which is very, very handy indeed. Otherwise, it'd be pointless having a rule, wouldn't it? So let's first of all rewrite our equation. So I'm going to use my space carefully. So we have 6 sine theta is equal to, notice it's equal, it's not an identity, 1 over cos theta. And you might be thinking, well, how on earth is that going to help us? Am I going to have to use, I don't know, square root of maybe 1 subtract sine squared? Something like that? Well, to get everything in terms of sine, perhaps, or a similar way to get everything in terms of cos? Well, the answer is no. We're just going to multiply by cosine on both sides. Let's clear that denominator so it looks a little bit neater. All right, so we're going to have 6 sine theta cos theta is equal to 1 if we multiply both sides by cosine. Now, the reason why we did questions 3 and 4 in the warm-up was for this definite eventuality. This was going to come up, and we can see this is identity spotting time. Is there an identity that I can replace all this with? Have a think. Well, you could pause the video if you like and have a go yourself. It's probably a good idea to do that, so I don't sort of ruin it all for you. But with a little bit of research, a little bit of thinking, you'll notice that this look very, very similar to this identity here. In fact, I keep doing this, but I'll use the theta so it's in the context of the question. Sine 2 theta identical to 2 sine theta cos theta. So how are we going to make that fit in the situation we've got? Because of course we don't have 2 sine theta cos theta, we have 6. Well, it's very simple, isn't it? If I just take my identity that I've got here and multiply both sides by 3, then you'll see very easily it's going to be 3 sine 2 theta is identical to 6 sine theta cos theta. It's just a bit of manipulation of the identity, isn't it? Okay. Right. So that's important. So therefore we have that. And we can put this back in to the question. So I'm going to now rewrite the question as follows. So this is going to be 3 sine 2 theta is now equal to 1. All right, that's really good. And let's divide both sides by 3. So therefore, sine of 2 theta is equal to 1/3. There we go. So that's rather good. And a lot of work's been done for us in this question already, but we'll go through, we'll keep going. And remember, of course, we are now solving this equation in the interval from 0 up to pi, but not including either of them. So we've got a sort of year 2 style trig equation because we're in radians here. So let's make a substitution. We're ready to go now. We've used up the new identities. So let big X equal 2 theta. So we now have, such that sine of big X is equal to 1/3. Let's do a principal angle. Principal angle, big X is going to be the inverse sine, which you now know is the arc sine of 1/3. And we did this in the previous question. So I'm just going to write it down now if it's fresh in your mind. The inverse sine of 1/3 was, of course, 19.47 degrees. Okay, and you might be saying, but we were told that the question is in radians. Well, yes, but we can convert to radians later on. Okay, so why don't we do that? Now we've got to make an adjustment of the interval. So I'm going to go up onto the right-hand side now. So we're going to adjust the interval, and we can convert it into degrees while we're doing that. Okay, so at the moment we've got 0 up to and including, up to and not including pi. In other words, it's 0 radians up to but not including 180 degrees. I think I said, did I say 0 radians? I meant 0 degrees. Okay, so that's just converting the radians into degrees. And now we have to adjust that interval. So we know, of course, that x is 2 theta. We'll do that in a minute, just to remember that from earlier. So we now got 0 degrees, double everything, 2 theta, and 360. So just double everything, it's 360 degrees. And of course, the interval we're working in is with x. So i.e., going to look for angles of x between 0 and 360 degrees. There we have it. And let's do the cast diagram now. So ordinarily, we would only go a half turn because it was from 0 to pi, but because it's a 2 theta inside the question, which we've converted from a theta, we now have to go twice as far, so we have to go up to 360. So we'll add the cast diagram here along the middle. So C, A, S, and T. And it was a positive value, wasn't it? It was a third, and it's the sine function again. So all and sine, the same stuff. 19.47 and 19.47. Okay, and we get our angle X really, really quickly. So reading off from the cast diagram, we will have that X would be equal to 19.5 degrees. Or in fact, I'll leave it as 47 until we convert it into radians. So 19.47 degrees. And we just have to subtract that from 180 now, which was 160.53 degrees. Okay, so that's what X is. So in other words, that's what 2 theta is, of course. So I don't want to write it all out again. Just remember that is 2 theta. So therefore, the theta angle, just divide everything by 2. So you can use your calculators for this, but I'll just do it as an aside. I won't do it on the screen. So theta is, of course, going to be 9.735 degrees for the first angle. And for the second angle, that's going to be 80.265 degrees. Okay, now just remember, of course, we've not finished the question. We now have to convert these into radians. The question was in radians initially. All right, so to convert to radians, just put a reminder. Remember, in previous lessons, I said write radians in big letters. You'd probably be aware of this now, so you don't necessarily need to do that, but make a note of it. So this time, theta is going to equal 9.735, and then you're going to multiply that by pi over 180. Okay? And it's just a case of simplifying that as a decimal, which we will do in a second. Okay, and then the second answer would obviously be 80.265. And then you're going to multiply that by pi over 180. Okay. So theta is going to equal. So again, just plug all this into your calculators, but I'll just give you the answers straight onto the board without bringing the calculator up again. So we'll get 0.170 for 3 significant figures. That's radians, of course. And the second answer, 1.40 radians. Okay, so I've just slightly gone over the space, but those are our final answers. If you're inclined to do so, of course, and this was an exam situation, you have the time, plug these answers back in to the equation and see if it works. Okay, you can always check your answers, and you know you've got enough answers because of the doubling of the range for theta means that obviously you're going to have at least 2 solutions. Okay, so that concludes that one, and we'll move on to worked example 3 now. Okay, worked example 3. This is the one I alluded to earlier in the warm-up exercise for question 2, I believe. And what's nice about this is you're given a little bit of a nudge. You're given a clue here by writing 3 theta here as 2 theta plus theta. Okay, so the question is, how are we going to get this identity just from that information? Well, if you notice it's additive, we're adding 2 different angles together. These are different. We have 2 theta and theta. They're different objects in the context of trigonometry anyway. We're not going to collect the like terms because, of course, collecting like terms will give us the 3 theta. So that's not the point, is it? So how can we use 2 theta plus theta with an identity to show the identity that's given? Well, again, if you want to do this, pause the video and have a go. And you'll hopefully find that compound angle identity should do the trick. So I'm going to make a note of it. Sine of A plus B is, of course, going to be sine A cos B plus cos A sine B. And notice when I write these out, I'm putting the A's and B's in alphabetical order all the way through. It's just for consistency. And you can look this up in the formula booklet. So in the context of this question, what we're going to do, well, we could simply make a substitution. So I'm going to say, let A equal 2 theta and B equal theta. And let's substitute in across the whole identity. So if I do that, we're going to have sine of, open a bracket, so that's going to be A, no it's not, we're substituting in, apologies. So it's going to be 2 theta plus theta. So I'm going to use different colors here to show the substitution. Okay, which, yes, we can collect those together to make 3 theta in a moment, but the ramifications of this are we have an identity, so we can do it on both sides. So I'm going to replace A and B on the right-hand side here. So A is going to become 2 theta in both those situations, and B is going to become theta in those situations. So let's do that. So we're going to have sine of 2 theta multiplied by the cosine of theta. Okay. And then we're going to add the reverse. So add the cosine of 2 theta multiplied by the sine of theta. And just double check that that's correct. You've substituted everything in the right order, in the right place, and it's consistent and it makes sense. Now, because we've done that, we look for any tidying up we can do. Well, on the left-hand side, we've got the identity sorted out, haven't we? So this is just going to simplify to sine of 3 theta, which is rather handy. So I'll just write that as 3 theta. So left-hand side is done. It matches what we were given or what we were asked to show in the question. On the right-hand side, it's a different story. We have a problem. Now, we can't collect like terms because these are non-similar objects. The sine 2 theta and the theta swap in each of the terms, so they're not the same object as I just mentioned. So what do we need to do? Well, the thing to notice is if you go back to the question, it's a show that question, and notice that each of the terms is in terms of theta only. There is no 2 theta at all. So what is this telling you? Well, it's telling you to use double angle identities. So we're going to have to use a double angle identity here and a double identity double angle identity here to break open the sine 2 theta and the cos 2 theta and have terms purely in terms of theta. So let's do that. So the first one is straightforward, I think. I'm going to start with brackets. I've only got one option with this. So this is going to be, of course, 2 sine theta cos theta for the first bracket, because there's the identity there. You can probably see it. Those two bits are identical. And that's going to be multiplied by cos theta. So I'll put that in. Okay. And for the second term, this is where we always seem to be running into a problem. It's which identity do we use? Well, without writing them all out again, we wrote them all out in the previous example. We have a choice of 3. But once again, notice everything is in terms of sine theta. Okay, whether it's cubed or not, it's sine theta everywhere. So I need to use the cosine 2 theta, which is in terms of sine theta only. So I'm just going to make a note that I strongly recommend you annotate this yourself as well. This is the problem solving aspect of this. So I'm going to use the sine theta only version. Now, if I use that one, that's the 1 subtract 2 sine squared theta for that. And then I'm multiplying that by sine theta. And once again, these two expressions are identical. Okay, even though I've not put it in different color, but never mind. And right, so now it's expand and simplify. Again, as the prerequisite stated, going back to those algebra skills from way back. So everything in the first bracket is going to be multiplied by cos theta. So I'm going to have 2 sine theta, and that's going to be cos squared theta when I've multiplied that. And in the second term, I'm multiplying everything by sine theta. So I'm going to have plus sine theta. Okay. And then I've got subtract, because it's a negative and a positive, 2 sine cubed theta, because we have a sine squared multiplied by a sine theta. Okay, I hope that's all right. So that's multiplying this with this. Right, are we nearly there? Is there anything we can collect together? Well, we still have a problem. We don't have everything in terms of sine yet. We've still got this in the way. So what do we use? Well, we go back to our trusted year one material for this one. We have a replacement for cos squared, which is purely in terms of sine squared. So we're going to use cos squared theta plus sine squared theta is identical to 1. So therefore, cos squared theta can be replaced with 1 subtract sine squared theta. And that's exactly what we're going to do. So that's a little aside there. I'll just mark that off as a little bit of extra observation. So let's continue with the question now. So we're going to, so this is all identical to 2 sine theta. And then I'm going to have 1 subtract sine squared theta, close that bracket, add sine theta, and subtract 2 sine cubed theta. And I bet you didn't think it was going to be this many steps. Okay, and let's expand and simplify once more. So multiply everything in the bracket in red by 2 sine theta. So that's going to be 2 sine theta, the first term, subtract 2 sine cubed theta. Okay. Add sine theta, subtract 2 sine cubed theta. Taking great care with your signs as well, as in plus or minus. Right, let's collect like terms. Well, the like terms in trigonometry are whether it's squared, cubed, power 1, and whether it's, of course, sine, cos, tan, or some other trig function. So we've got sine theta there, plus sine theta there. So that's 2 plus 1, which is, of course, 3. 3 lots of sine theta, first of all. Okay. So we collected those together. And then we've got sine cubed. So we've got negative 2 lots of sine cubed. So we'll just collect those together. So sine cubed there, sine cubed there. So we've got negative 4, or subtract 4. Oops. Sine cubed theta. So let's check. Is that what we wanted? Yes, it is. Okay, and it's in the correct order. So we seem to have, we've shown that. And just to recap, we started off, just want to review what we've done here because there's a lot going on in this question. So we started off here with using the compound angle identity for sine, because it's sine 3 theta we wanted. That forced us to have a expression on the right hand side in terms of sine and cos with 2 thetas and thetas. We then used the double angle identities to break open those 2 thetas. And then if there was any cosines in the way, we could use the Pythagorean identity from year 1. And that allowed us to write everything in terms of sine, which is what we wanted. And lo and behold, we've got the answer. All right, so I hope that's okay. And that's part A. So it's quite a long question, this. And for part B, it says hence or otherwise. Now, I've taken this from an exam context. If you see hence or otherwise, remember what to do. Cross out the or otherwise bit. Okay, please always use what you've just found or what you're asked to show. And if you didn't successfully show it, use it anyway to gain some marks. So for part B, we have to solve this awkward looking equation. So I'm just going to write it down. So it's 12 sine theta subtract 16 sine cubed theta is equal to 2. So how does this fit in with what we've just found? Well, you'll notice it's almost the same, isn't it? There's just these, it's 3 and 4 here, And unfortunately, we've got this pesky 12 and 16 here. Well, that's okay. It looks like the whole thing's been multiplied by 4. Okay, so it's the same as 4 lots of what we had earlier. So that was 3 sine theta subtract 4 sine cubed theta. So that's the first thing to notice, which is equal to 2 in this situation. But also, we now have a different way of writing this rather nasty looking expression, don't we? So all this can now be replaced with the rather nice sine 3 theta. And when we're solving equations, the sine 3 theta is really good. So just means we have to adjust our interval. So this is just going to be 4 lots of sine 3 theta, okay, which is now equal to 2. All right, and if you got to that step, you're on your way. So to finish that off, so that's going to be sine of 3 theta is of course going to equal a half. Great. Now we've now got to solve the equation, and it's in the interval from 0 up to pi. And you'll notice because we have 3 theta over here, we're going to have to adjust the interval. So we'll get the principal angle out of the way first, and then we can adjust the interval in a moment. So principal angle, I'm just going to partition this off so we don't get muddled up. Principal angle. All right. Now, what I probably should have said, let's let x equal 3 theta as well before we get ahead of ourselves. And we do the inverse sine of a half. And I think we should work in degrees as well, which is, of course, 30 degrees. So that's nice. Okay, so we've got our principal angle. Now we adjust the interval. Because we've already done this, I'm just going to adjust it straight away. I'm not going to put any steps in. We simply, we're going to use the interval for the angle x. And we have to, because it's theta between 0 and pi, it's effectively theta between 0 and 180. And I have to triple everything. So you'll find that it's going to be from between 0 degrees, x not inclusive as well, and then we have to multiply everything by 3, which will give us 540 degrees. I hope that was not too much in one step. Okay, so it's just multiplying everything in this interval by 3. Okay, so 3 times 0 is 0, 3 times theta is 3 theta, which we're calling x, which is here, and 3 times pi, which is 3 times 180, which is 540. So essentially we go around the cast diagram 1.5 times. And speaking of which, let's draw the cast diagram now. So slightly odd looking one there. So C, A, S, and T. It was a nice positive sign value, of course, which puts us in the all and S category. If we just add the angle on, so that's going to be 30 degrees, no decimals to worry about here, which is good. 30 degrees, and we just read off. So we go around 1.5 times. Just as a reminder, of course, we're going to start at 0 degrees and we go anti-clockwise. So x angles. So x, if we go around 1.5 times, we're going to have 30 degrees, 150 degrees, that will take us up to the 180 mark. There's no angles between 180 and 360, and that's a full turn. But we do have 2 more angles to add in. And that's really simple. So they're basically 360 more than what we have already, which will give us 390 degrees, so adding 360 to that, and then 510. Which is, of course, that's 30 degrees less than the 540 mark, which is 1.5 turns. So we've got our x angles. So that's really good. Remember that the x angles are equal to 3 theta, and we know we've gone round enough times. So our angles for theta should fit neatly between 0 and pi radians. So let's do that. So for theta, just like changing color, just simply divide everything by 3. So we're going to have 10 degrees. $50 degrees, 130 degrees, and 170 degrees. Okay, so those are my thetas. All in terms, sorry, I beg your pardon, all as degrees. So we now need to convert these into radians. All right. So let's do that. So theta. So multiply once again by pi over 180 for each one. Now, again, I'm just going to do this in one step. So I hope that's all right. So I don't want to take up too much more space or time on this. So essentially, we've got 10 pi over 180, which is going to give us pi over 18 for the first one. That's what 10 degrees is in radians. I don't know why it's in red, but never mind. For the next one, it's going to be 5 times that. So that's 5 pi over 18. So it's just 5 lots of 10 degrees, isn't it? So 5 times pi over 180. And then 13 pi over 18. They're co-prime, they don't share common factors. And 17 pi over 18 as well. All right, and we have 4 answers. So I hope that's okay. So it's quite a complex question there, lots going on, but that concludes it. And for the final worked example, we have a rather complex looking equation here. We have got a sum, which looks rather nasty, and we have a surd in that second term. At the moment, it looks like this isn't going to be particularly easy to solve, but we've got identities we can use, and we have a rather nice looking interval to be working with, and it's in degrees as well, which is always a bonus. So the first thing is, what do we need to consider? Well, we need to consider the fact that we've got the sum of 2 angles here, one of which is an unknown, and we're dealing with both sine and cosine functions. So we need some way of getting the trig function either as a sine of theta or a cosine of theta. Then perhaps we can collect like terms and solve the equation. At the moment, we can't do that. So this is where the identities come in and why they're so powerful. So thing to notice is this identity is going to play a part. So it's the sine of a plus b is, of course, sine a cos b plus cos a sine b, like that. And in this situation, I think it's pretty clear. We've got a is going to be theta, representing this one, and b is going to be obviously 45 degrees over here. So we're going to replace the A and the B with theta and 45. So let's do that all the way across, and we can see what happens on the right-hand side of the identity. So this is going to be the sine of, and again, I'll use colors to make it a bit easier. So that's going to be theta plus 45 degrees. Okay, this is probably a point where you want to speed me up on YouTube. Okay, and that's identical to, and we're going to put theta and 45 all the way across. So what I'll do, I'll leave gaps. So it's sine, cos, plus cos, and sine. You'll see what I'm doing now. So I'm going to put the thetas in first. So A is, of course, theta. And B is 45 degrees, 45 degrees. Okay, and that first term is a product, of course. I think maybe I should just adjust that slightly, cos 45, so it looks more like a product. Oops. I'm supposed to save time there, but obviously I've not done that. Cos of 45 degrees. There we go. And what can we do with this? Well, cos 45 and sine 45, of course, have values, don't they? If you don't know what they are, you can use your calculator to draw a triangle. It's a standard, one of the standard results here. So I'm going to replace those with their values. So this is going to be identical to sine theta multiplied by 1 over root 2. And then you're going to add cos theta, again multiplied by the same value, which is 1 over root 2. They happen to be the same because it's the isosceles right angle triangle that they come from. There we go. And you'll also notice that we have an unrationalized surd here, and it's probably a good idea to rationalize them because we have what looks like a root 2 in the numerator, in a possible numerator up there. So I'm going to rationalize these, and I can factor it all out if need be. Maybe I won't do that. I'll just leave it as it is. So it's going to be root 2 over 2 sine theta, okay, plus the same thing again, root 2 over 2 cos theta. Now then, we'll take a step back and see if this is helpful. Right, now we've broken open the theta plus 45 within the sine function. We're in good shape here because we've got sine theta and cos theta, and we've got the cos theta over here waiting. So we can put all this back into the equation. So in the equation, sub everything in, see what happens. So we're now going to have root 2 over 2 sine theta plus root 2 over 2 cos theta. And then from the equation, subtract 5 root 2 cos theta is equal to 0. Okay, good. Now we can collect some like terms that, now we've done this, because you'll notice we've got cos thetas here and here. So I've got root 2 over 2, subtract 5 root 2. Well, if we think about this, the object we're interested in is the root 2, isn't it? So you could even think of the objects as root 2 cos thetas if you like. So in other words, just as a little aside, if you want to do this in your head, so if I let big X equal root 2 cos theta, then the situation I've got is essentially a half x, because it's root 2 over 2 cos theta, subtract 5x, which of course simplifies to negative 4.5, which is negative 9 over 2x. All right. I hope that makes sense, guys. So that's going to be my next step. You could, of course, do it on your calculator, of course. So we've now got root 2 over 2 sine theta. And then it's negative now, so subtract 9 root 2 over 2 cos theta is equal to 0. So where can we go from here? Well, we've still got the problem of the sine theta and the cos theta, but the equation is equal to 0, which is a bonus. So if I can perhaps do some factorization, I might be able to set up some equations using those factors. Well, the first thing I can factor out, you'll probably be able to tell, is we've got root 2 over 2 as a common factor in both terms. So I'm going to take those out on the outside. So we'll factor those out. Notice I never divide by anything. It's better to factor things out because it's a good habit, because if you're factoring out variables, or let's say the opposite, if you're dividing by variables, you could be dividing by 0, because the variable could take the value of 0. And that's what you're not allowed to do. So it's a mathematical fallacy when you do that. But if you factor them out, that avoids that problem. So we've got root 2 over 2 as my common factor. And then inside the bracket, I'm going to be left with sine theta subtract 9 cos theta, close the bracket, is equal to 0. And this is where your eyes should sort of light up, because this is a product of root 2 and whatever's in the bracket. And root 2 over 2, sorry. Now, root 2 over 2 is never going to be equal to 0. So this implies, and in fact, I'm going to continue up here on the right-hand side. So all this implies that, forget about the root 2 over 2 now, that sine theta subtract 9 cos theta is equal to 0. After all that work, it looks a lot nicer, doesn't it? The problem is, though, how do we solve this? Because we've got two different trig functions, but they are connected. Recall. How are they connected? Well, there's the Pythagorean identity, but there's also this one, the tan function. And we've used this trick before, haven't we? So if we divide our equation by cos theta all the way across, let's see what happens. I'm going to divide every single term by cos theta. Okay, and if we do that, the first term is going to, of course, be tan theta using the identity. The cos thetas will cancel in the second term. Subtract 9, and 0 divided by anything is, of course, just 0. So we now have the situation where tan theta is equal to 9, which is fine. The range of tan is, of course, all real numbers. All right, and we solve this equation. Nothing scary about it. In the interval 0 to 360. So we can write down a principal angle cast diagram, and we're done. So we do the inverse tan of 9, which won't be a particularly nice answer. I'll just do this on my calculator. You can use your calculator for this. I won't do it on the board. So that's going to be 83.66 degrees. That's to 2 decimal places for now. And on the cast diagram, we just draw that. We can find out if there's any other solutions. Well, there usually is, isn't there? C, A, S, and T. 9 is a nice positive number, so we're going to look for where tan is, of course, positive. So it's always positive in all. And T, let's put the angle on there. Oops. So let's put that, try again. So that's going to be 83.66 degrees on both sides. And we just read off our angles. It's in degrees, don't have to convert to radians, anything like that. So theta is going to be 83. Let's round these to 3 significant figures now. So that's 83.7 degrees, and simply add 180 to that to get the final answer, which is, of course, going to be 263.7 degrees. So I think that does it. Those are our final answers. Make sure they're rounded. Well, I've done the second one to 1 decimal. Well, I think 1 decimal place is better, isn't it? In this situation, it doesn't actually specify an accuracy. Okay, I think that concludes that. So yes, that's the lesson finished.